So today we'll start a new chapter, chapter 5, and chapter 5 is steady state sinusoidal analysis. And the steady state sinusoidal analysis, or simply AC circuits. So at the beginning of this chapter, we need to define, or we need to differentiate between two types of circuit. So the first type of circuit is DC circuits. So DC circuits means direct current, and direct mean one direction. So if we have a voltage source with polarity positive and negative, so this terminal will be positive and this terminal will be negative forever. And if this voltage has a value, say 5 volt, its value will be constant at 5 volt. So if we sketch the voltage between point A and point B, this voltage here VAB, if we sketch this voltage VAB with respect to time, we will see that the voltage is constant at positive 5 volt. And if we need to sketch the voltage between B and A, if we need to sketch the voltage VBA versus time, it will be constant at negative 5 volt. This is what we call a DC source. So DC means the value and the polarity are fixed. but this is not the only DC. So if the DC is constant, we call this pure or ideal DC. However, there is another condition to say that the voltage you have is DC. So what is the condition to say that the voltage you have is DC? If the voltage you have has an average, we can call this as DC. So if we sketch a voltage versus time, and this voltage was something like this. So the voltage here is not constant, but if you take the average of this voltage, you will see that the average is not zero. So the average is not equal to zero. So we call this again as DC. So you will have a DC if you have a non-zero average. In this case, the oscillation around the average, we call this ripples or harmonics. So these ripples or harmonics means you have a distorted DC, not a pure DC. And this is a typical case that we will have in real life, that the voltage will have some oscillations, which we call it ripples. This pure DC is kind of ideal, and this is how we study our DC circuits. So this is the first type of sources that we studied so far, is DC circuits. So we can assume for DC circuits that the value is constant and it's equal to the average if we are assuming that these ripples are very small. In this regard, the change of the value of the DC with respect to time can be approximated to be zero. Okay, so here we defined what is a pure DC or ideal DC, and what is a practical DC, which has some oscillations or some ripples. Now let's go to the AC. Alternating current. So the alternating current or the alternating voltage, so if we go back to our source and we say here terminal A, terminal B, and we will sketch again our voltage VAB, and we will sketch our voltage VAB versus time to see how the voltage VAB will change with time. In case of AC, for example, we will see the voltage will be something like this. So the voltage is positive, so this means you have a positive negative here for certain amount of time. Then after this time, your voltage will be negative, which means at this time here we will have a negative and positive. Then, sorry, negative and positive. Then at this time again, we will go back to our positive negative, our positive negative. And the polarity will keep flipping after each time t, after each time t. Let's name this as t over 2, t over 2, and so on. So after each time, the wave will flip, and it's a kind of periodic wave. In this case, if you look at the average will equal to 0. In this case, we will call this as AC wave, and we give it the symbol of AC. So AC source means your polarity, or the direction of the voltage, or the direction of the current, is not constant with time. Actually, the current is changing direction after each half cycle. So we call this T over 2 as half cycle, as we will see later on. And AC voltage doesn't have to be a pure wave. So what is a pure or ideal AC, which is the voltage we have at home? So if you look at the voltage versus time, it should be a sine wave. So this is the ideal voltage. So if we look at the time, the voltage value is changing with time, increasing until it reaches a peak. Then this value is decreasing until it goes to 0. Then the polarity change. So if you look at the plug you have, or the outlet you have at your home, and if you connected a voltmeter across this outlet, and you start to see what is the voltage you see versus time between this point A and this point B, you will see at the beginning A is positive and B is negative, and the voltage magnitude, or the value you are reading here, is increasing until it will reach a maximum value. Then it will fall again and it will reach 0. Then you will find that the polarity of the voltage is reverse, or you are reading here a negative value. So you will start by reading a positive value, and this positive value will be increasing. Then you will start to read a negative value, and this negative value will be increasing, and this will be repeated. In this case, we call it pure AC. So pure AC is a sine wave, and the positive wave equal to the negative part, or the positive half cycle equal to the negative half cycle. So you will have a 0 average, and this is what's called pure AC. In real life, the practical AC, if we sketch the voltage versus time, it will be something like this, which has some harmonics. It's a sine wave, but this sine wave is distorted and it has some harmonics. So it has harmonics. So harmonics means the distortion in AC, while ripples means a distortion in DC. So the distortion or the oscillation in DC, we call it ripples, while the oscillation in AC, we call it harmonics. However, we can assume in AC that we have a pure AC. So in AC, we will assume that we have a pure AC or ideal AC. In this case, the voltage or the current will be sine waves. So the voltage or current will be sine waves. But the question is, why sine wave? Why in AC we had sine wave? Why Tesla, when he proposed his AC system versus the DC system, he proposed a sine wave system? So let's see how we can generate electricity. To generate electricity, we use what is called a generator. So let's bring this photo here. So this is the construction of the generator. So what we have inside the generator we will have two magnets. So this is, or one magnet. So we'll have a north pole and we will have a south pole. So this is a magnet, and this magnet is creating what is called magnetic flux, which we will call it or give it the symbol phi. So phi means magnetic flux. The density of this flux, or how many flux lines we receive per area, how many flux lines you are receiving across this area, we call it B, or we call this the flux density. And the flux density equals the flux divided by A. And inside this coil, inside this magnet, we insert a coil from a conducting material. Okay, so what we have here is called coil, and this coil is from conductors like copper, aluminum. And then what we will do, we'll start to move or rotate this coil inside the magnet. If we have a coil or a conductor cutting a magnet, according to Faraday, we are generating a voltage. And the amount of the voltage generated, which we will call it E, this is the generated voltage, equals to B L V sine theta. So B is the flux density, which is how many flux lines you receive from the magnet per square area. L is the length of the coil, so this is L. It's the length of the wire you have. V is the velocity that you are rotating this coil, so V is the velocity. While theta is the angle between the coil plane and your magnet. So if this is the coil here, let's change the color. If here this is the coil, so the coil plane, which is this rectangular here, will have a direction going up, making a 90 degree. The direction for the flux is going north to south, so this is the direction of the flux. So on this position, the angle is 90. But this coil here is moving, so this angle theta actually is changing from 0 up to 360 degree. So what you have now, you have the generated voltage equal to a value. B is a scalar value, L is a scalar value, velocity is a scalar value, while theta is variable with time. So theta is actually your omega, your speed in radian per second multiplied by t. So your theta is changing with t, so omega t or this theta changes from 0 to 360. So what you are generating on this coil between these two terminals of the coil, you are generating a voltage. And this is how we generate voltage. So the generated voltage will have the following function. So the voltage we are generating equal to a maximum value multiplied by sine theta. So the voltage generating here is a sine wave or sinusoidal. Sorry. So the voltage generated is sinusoidal, and this is the only form that we can generate for voltage. So the DC voltage, actually, the internal design of the generator is the same as AC, but with just a little change between AC and DC. And this is where Tesla contributed, because before Tesla, we had a DC generator, but internally, this DC generator was actually AC. The only way to generate electricity from a generator is to generate a sine wave. So here is the positions of the coil. So if the coil is horizontal, we saw that the angle theta will be 90. And when the coil is vertical, the angle will be theta will be 0. And then this coil will go back horizontal. So the angle will be minus 90. And then it will go again vertical, and the angle will be 360. So if we need to sketch how the voltage changed with the value, so when at the beginning when theta is 0, your voltage is maximum. And then when theta is 0, the voltage will be 0. Then when theta is negative 90, your angle will be, or your value will be negative V max. then when theta equals 360, your voltage will go back to 0. So if you sketch this, you will have a cos wave or a sine wave shifted. So this is E and this is T. So what we have here is the AC voltage. So the voltage will be between negative E max and E max. And the function for this voltage is actually a sine wave. However, what if this coil didn't start at position 0 or position 90? So you turned it off the generator and the coil stopped at any angle. So this coil stopped at any different angle. So to account for the initial position of the coil, we will say that the voltage V of t or E of t equal to a max voltage sine theta plus an initial angle, And instead of writing this as theta, let's name it from now as omega t. And this equation is the general equation for any AC source. So the AC source voltage is not constant. The voltage is function of time, and it is changing with time following a sine wave or a sine function. Let's add a page here. Now let's see how the sine wave, or what are the important values on a sine wave. So the general function or the general equation for V of t, that V of t equal V max sine omega t plus the initial angle, which we will name it from here on as theta. So what are the important values in this wave? So if we need to sketch this sine wave, this is what we will have. So what we will have here, so what we will have here is V of t, here is a time t, and this value here is the maximum value V max, and this value here will be negative V max. What we have here is 90 degree, but we have here, so this is pi over 2, this is pi, and this is 3 pi over 2, this is 2 pi, and so on. So this is a complete sine wave. This wave here starts at 0, which means that theta initial is 0. So what we have here is V of t equal V max sine omega t. So when the time is 0, your voltage is 0. There is no shift here. But this wave can be shifted. So what if this wave was shifted? Or we have an initial shift here. So let's say here is the wave, but let's assume there is a shift. So if we assume there is a shift, so assume this is your y-axis, okay? So this is where the time is, your axis. So this will be the voltage if your wave is shifted. So if your wave is shifted with certain angle theta, and this theta, by the way, can be positive or negative. So this axis can go this way, or this axis can go this way. So we call this theta as shift, or our sine wave is shifted. So the general equation for V of t, or the voltage as function of time versus time, that V of t equal V max sine omega t plus or minus theta, and plus or minus theta is called phase shift. Now let's take an example. So if we have a voltage V of t equal to 150 sine 20t plus 30 degree. Okay, this is how the voltage will be represented in AC circuits. So what is the meaning of having this kind of voltage? So the meaning of this, that the voltage maximum value is 150, and there is a phase shift of 30 degree. This means that your voltage will be zero not at t equals 0. It will be 0 when this angle omega t equal to 30 degree with negative angle. So your wave will be 0 at negative 30 degree. So if we need to sketch the sine wave, so here negative 30 degree, and your wave should be starting with 0 at negative 30 degree. Then this will be your wave. So this is V of t, here is t. So the voltage will start from this value here. So this value is simply V max sine 30 degree. When you put t equals 0, it will be V max sine 30 degree. So your voltage will not start from 0, but it will start from a value, then it will go to a maximum value of 150, then it will go back to 0, then it will go back to a maximum value of negative 150, and go back to 150, and so on. And this is the sine wave. So this is the meaning of having a voltage with this equation. Now let's take a general sinusoidal waveform. So what is a general sinusoidal waveform? So let's say this is a general sinusoidal waveform. We said that this value will be Vmax, and this value here will be negative Vmax. The time you will take to complete one cycle, positive, negative, we call this time t, or cycle time. So the cycle time, or the period of the wave, is t, and this is the time to complete one cycle. And this cycle time t, or this angle t, if we multiply it by omega, this will equal to the angle in radian per second, or this is the complete cycle, or 2 pi. So the relation between omega and t is this equation, that omega t equal 2 pi, or t equal 2 pi over omega. So this is the first important equation we have here. So the first important equation we have So the first important equation we have, that the period time equal 2 pi divided by omega, and omega is called the So the first important equation we have is t equal to 2 pi over omega, and omega is the frequency in radian per second. So omega is the frequency in radian per second, and the t is the period, or the cycle time, and t is measured in seconds, and omega is measured in radian per second. The frequency f, which is how many cycles you make per second, will equal to 1 over the time you take to make one cycle. So f, which is cycles, has a unit cycle per second, or we give it hertz, equal to 1 over t. So f equal to 1 over t, or f equal to omega over 2 pi, or we have omega equal to pi f. This equation will convert the frequency from hertz, or cycle per second, to radian per second. These are the two units for frequency. So let's take an example, the voltage you have at your home. So at your home, you have a voltage V of t equal, what is the function we have? So the voltage at your home is 110. So we will do here a little bit of a mistake that we will correct later on, but let's say that the maximum voltage you have is 110 volts and the frequency you have at your home is 60 hertz, which means your omega is 120 pi radian per second. So if we need to write down the equation of the voltage at your home V of t, it will equal to 110 sine 120 pi t omega t plus angle theta. And the angle theta is the time at which you will connect your load to the plug. So you will connect the load to the plug at certain instant. So the voltage of the plug is changing with time, but at which instant, at which theta, you will connect to the supply. So what we covered now is what is meant by having an AC voltage. So what is an AC voltage and how we can represent it. Now let's continue. So what is the meaning of having a voltage V of t equals to 100 cos 50t minus 120 degree? So this is a typical voltage for a sinusoidal or AC voltage source. So how we can deal with 100 cos 50t minus 120, or what is the meaning of having a source with this equation? So this means that the maximum voltage, that V max equal to 100 volt and omega equal to 50 radian per second. And if omega is 50, we can calculate t and we can calculate pi. Sorry. So if omega is 50 radian per second, so we can say that frequency equal omega over 2 pi equal to 50 over 2 pi, and the unit is hertz. And t equal to 1 over f equal 2 pi over 50 in seconds. So all these three are the same type of information but different units. And here our theta is minus 120 degree. This means we have a cos wave shifted by minus 120 degree. So if we need to sketch so minus 120 degree means positive 240 degree. So when your cos wave will equal to 0, so when your cos wave will equal to peak. So your cos wave will equal to peak when omega t, or the angle, is positive 120 degree. So if the angle is positive 120 degree, you will have cos 0, which is 1, which will give us the peak. So here is the peak, 100 volt. And this will happen at an angle of 120 degree. In this case, your voltage will be peak. Then the voltage will go down to 0. Then the voltage will go back to negative 100 volt. And the voltage will go back again to 0. And this will be a sine wave. And here, for the voltage to be 0, we need the angle here to be 90, and this will happen when this omega t will be 30 degree. So this voltage will go to 0 at 30 degree. It will be 0, and it will continue like this. So this is the voltage V of t versus time. Now if we take the time from here to complete one cycle, this time t will equal to 2 pi over 50 seconds. Also, instead of writing this equation as a cos wave here, we can write the same equation as a sine wave. So how we will write this equation as a sine wave? You know that sine 90 equal to cos 0. So if you have a cos wave and you need to get its sine version, you need to add 90. And if you have a sine wave and you need to get its cos version, you have to subtract 90. So keep in mind this simple rule so you can know how to move from sine to cos and vice versa. So we can write the same equation as V of t equal to 100 sine 50t minus 120 degree plus 90. So we can write this equation as 100 sine 50t minus 30 degree. And if it is a sine wave, you look at the zero, not the peak. So as the zero, it's shifted by 30. So as a sine wave, it's a sine wave shifted by 30. But as a cos wave, at the cos, you look at the peak, it is shifted by 120 degree. So we can write any voltage as sine or cos. The difference will be how you shift the angles. So let's take another example here. So what if we have V of t equals to 350 sine 120t minus 30 degree. So this means that your maximum voltage V max is 350. Your omega is 120 radian per second. And if this is omega, we know that omega is 2 pi f. So f is 120 divided by 2 pi in hertz. And t is 1 over f. So it's a 2 pi over 120 seconds. And this is a sine wave shifted by 30 degree. So if we need to sketch this waveform for the voltage, so here it's a sine wave, so it starts from 0 and it starts delayed by 30 degree, then it will go to peak, go to 0, then peak, and so on. And this will be the voltage. This is V of t, here is time, and the maximum value is 350 volt. The time that you will take to complete one complete cycle, this time here will be 2 pi over 120 seconds. The time to complete half cycle will be this value divided by 2, so it's a pi divided by 100 seconds. As angles, if we start here at 30, 0, so here is 30 degree, here is 120, here is 210, and so on. And we can write the same voltage here. We can write this voltage as a cos. So same voltage can be written as V of t equal to 350 sine 120t. Sorry, instead of sine, we will write it as cos 120t negative 30, and we will subtract negative 90. Again, why? We know that sine 90 is 1 and the cos 0 is 1. So to move from sine to cos, we subtract 90. So this value that V of t equal to 350 cos 120t negative 120 degree. This means that your cos will be peak at 120 degree. So if you sketch a cos with a peak at 120 degree, here is at 120 degree is your peak. So actually you will sketch the exact same function, this function here. So this function here can be written as a sine or as a cos. So I will stop here the lecture and I will continue part 2. So now we will continue with our first lecture on AC circuits. And now we will see how we will deal with AC voltage and what are the values we will use to measure AC voltages. So first, for DC voltage, we use the average. And to use the average, we have a device called voltmeter. So if you have a DC outlet and across this DC outlet you connected a voltmeter, this voltmeter will give you a value, and this value is the average of the waveform. So what is the average, or how this device is working? So if your voltage versus time is changing, but it has an average, so how the device will work? The device will calculate the average by finding 1 over the duration of the waveform multiplied by the integration of the waveform. So this waveform is f of t, and you will find the average over time t, assuming that this waveform is periodic and it is repeating. So these devices or the voltmeters actually will give you an average. In the case of AC, so if we have a source with two terminals and across these two terminals we connected the same voltmeter. So this voltmeter will give us the average, and we know that the average for AC is 0. So if you connected a voltmeter that measures the DC value or the average value on an AC source, it will give you 0. So usually you will find on the voltmeter there is a DC symbol. This DC symbol means it measures the average. So measuring the average for AC will have no meaning because the average of any AC is actually 0. So for AC, instead of using the average, we define a new value, and this value is called RMS. So any AC value will be defined by the RMS, not the average. So the RMS is the root mean square. So RMS is an abbreviation for the term root mean square. So what is the RMS? So from the definition, it's root average or mean square, so it is the square root for the mean. Mean means the average 1 over t integration from 0 to t, but not for the function, but for the function of t squared dt. Now when you square the function and the function is positive and negative, the negative will be squared and it will be positive. Now it will not cancel the positive, but it will be added to the positive. In this case, you will not have a 0 value for AC, but you will have a finite value in this case. So let's see how we can calculate the RMS for an AC voltage. So RMS for AC voltage. We said that the AC voltage will be a sine wave. So the AC voltage is a sine wave. So let's say that V of t is V max sine omega t. How we will calculate the RMS or the root mean square? So we will calculate the RMS. So V RMS equal to root. So root, here is the root. The second step is mean. So the mean is 1 over the duration is 2 pi integration from 0 to 2 pi. So if we sketch a sine wave, V of t, here is time, and it's a sine wave, here is pi, here is 2 pi. So the duration we are integrating over this duration is 2 pi. So the mean will be 1 over the duration 2 pi multiplied by the integration from 0 to 2 pi. And the third step here is to square the function. So we will take this function and square it. So it will be V max square sine square omega t. And we know that sine square theta is actually half 1 minus cos 2 theta. So we can rewrite this equation or this integration as VRMS equal to square root for 1 over 2 pi integration from 0 to pi, and we can take V maximum squared out from the integration, and we can substitute for sine square as half 1 negative 2 cos omega t. So here we will multiply by 2 because of the half, and we are integrating 1 negative cos to double theta d theta. This will give us square root for V max square divided by 4 pi, and the integration of 1 is theta, and the integration of cos 2 theta is sine 2 theta divided by 2, and we are integrating from 0 to 2 pi. Let's copy this equation here. Let's add another page. So this is what we have for VRMS. So we can take V maximum over 4 pi outside the integration. So we have our VRMS equal to V max divided by 2. And here we have inside 1 divided by pi. So we took V max square over 4 outside the square root to be V max over 2. Here we will substitute for theta as 2 pi. So we substitute for theta as 2 pi, negative sine 2 multiplied by 2 pi over 2 is 0. Then we will substitute by 0 minus 0. So here pi will cancel pi. So VRMS will equal to V max divided by square root 2. And this is an equation for the RMS and maximum relation for a sine wave. And this equation is true for any sine wave. So any sine wave, its root mean square will equal to its max, its maximum value divided by square root 2. And this will be the value that we will use for sine wave. You don't have to do the proof, but just we did the proof to understand how they came up with this relation that we will use later on for calculating the RMS. So any voltage value will be given as RMS. For example, the voltage at home is 110 RMS. So this 110 voltage is RMS. If you remember at the beginning, we did a mistake when we defined the voltage at our home, and we said we will correct this later on. So when we did the example for the voltage at home, we said that the voltage at home with 60 Hertz will be the voltage at home with 60 Hertz will be 110, but this was not correct. So we did this at the beginning as an assumption, and we said we will correct this assumption later on. Okay, so now we are correcting this assumption now. So the voltage at home, which is 110, this voltage is RMS. So V maximum at your home is actually 110 square root 2. So if you need to sketch the waveform for the voltage you have at your home with time, it will have a frequency of 60 Hertz. So the time here, T will be, so your F is 60 Hertz. So omega is 2 pi F, it's 120 pi. And T is 1 over 60 seconds. The peak value or the maximum value you have at your home will be 110 square root 2. So any value in AC will be measured as root mean square. That's why in the voltmeter, while you are selecting which setting you have, you will find this option and you'll find another option here. This option is DC and this option is AC. So if you put the voltmeter or the ammeter on DC, this means you are measuring the average. But if your selector here is at the AC, this means you are measuring RMS, or your device, your meter will calculate the RMS. So for DC we'll use the average, and for AC we use the RMS. The question is why RMS is needed and why we use the RMS for all AC circuits. We are not using any other value, we are using only the RMS. Now let's take an example. What if you have a resistance R, and across this resistance R you have an AC voltage V of t. This AC voltage V of t is V max sine theta. It's a sine wave. And now you need to calculate the power P of t in this resistance. Why we named the power as P of t? Because the power will be variable. Why the power variable? Because the voltage and current variable. We know that the power equal VI, and we know for resistance that I is V over R, so we can write this equation as V square over R. So the power as function of time equals to V of t squared divided by R, or equal to V max squared sine square theta divided by R. So if we need to sketch the power will be a sine wave squared. So the power will be always positive. P of t, here is t. So the power will be always positive because it's the square of a sine wave. But if the power is variable, what we need to calculate, we will need to calculate what is the power average. This is what is important. So if you are giving your load a variable power, your load will care about the average. What is the average power you will give to the load? Because if you multiply this average by the time, you will get the energy, which is the area. So how we will get P average? So how we will get P average if the power is function of time? So P average will be 1 over t integration from 0 to t P of t dt. So the average is 1 over the duration multiplied by the integration, or the area under the curve. So to get P average, we will integrate P of t from 0 to t, and we will divide over the periodic time, or over t. Now if we apply the equation here, P of t will equal to 1 over t integration from 0 to t, and the voltage or the power will be V of t squared divided by R dt. So we can write down that P of t, sorry, this is not P of t, this is P average. So we can write down that P average equals 1 over R multiplied by 1 over t integration from 0 to t V square of t dt. If we name this term as A, so P average will equal to as A squared. So P average will equal to A squared divided by R. So to calculate the average power, square this term A and divide it by R. So what is this term A? So this term A, so we defined all of these as A squared. So the term A will be the square root for 1 over t integration from 0 to t V square of t dt. So this term A is the root for the average or the mean of the function square, which is the RMS. So we can write down that P average equal to V RMS squared divided by R. And this is the importance of using the RMS, is to calculate the average power directly without going to integrate the waveform. And we can do the proof that P average also can be calculated as I RMS square R. So the power is I square R or V square R. So for AC, you can use the same forms that we used for DC, like power I square R or V square over R, but given you are using an RMS value or root mean square. So if you have a resistance, and this resistance has a value of 120 ohm, and this resistance is connected at your home where you have your VRMS, say, is 120 volt. Now, if you look at the power you have at your home, if you connected this resistance, or what is the power in this resistance or this heater, if you connected this heater at your home, the power will be variable. But what you care about is what is the average power that this resistance will take. So to calculate P average, you can simply say that P average is VRMS squared divided by R equal 120 squared divided by 120 equal 120 watt. And this is what you will write on this heater. So if you have a heater which has a coil inside, and this heater is 120 ohm, and you will connect this heater at your home, So you can write down on this heater that this heater is 120 watt. How you will calculate this 120 watt or the average power? By using V RMS of the outlet you have at your home divided by R. And this is the importance of using the RMS, is to calculate the average power directly without having to integrate or finding the integration. So I will stop here this lecture and we will continue next lecture. So please review the details in this lecture. So this lecture is actually just to define what is an AC voltage and what is an AC current and what is the value of, or what is the meaning of an RMS and how we can calculate it.